Last day of camp, chat. If you're feeling comfortable with Python and you're gonna be using stuff from this camp going forward, then that's great. It might be a little further. I might not be there where it's like, I can't say I'm comfortable, but I'm definitely in a better position to tackle it seriously, for real. If you're just under that 50th percentile, that's still great because you're here. You're here, you made it through all of camp. It took me not just a month or 7 days of a boot camp. It took me a good year, a good 2 years before I truly was able to say like, hey, I know something that I think other people don't, or I have information that is helpful to someone else. Remember, join the Discord, making new friends, and especially friends here from the camp. Let's do homework. Using random state 10 for the train dataset and random state 20 for the test dataset predict ERA. In the test dataset, using strikeouts per 9, walks, home runs, and FIP, using linear regression. Not worded the best, but you know what I mean. Visualize your prediction showing actual ERA on the x-axis and predicted ERA on the y. Display R² and RMSE in your graph. Okay, we have ERA loaded in. This is our handy dandy ERA, a data frame we've been working with on the back half of this. Okay, let's make a train data set. And we're gonna go ERA sample. And then let's just sample 100 of these. I'm gonna do random state equals 10. And we'll do another one here for test. And then we'll do random state equals 20. Okay. So here's our two random state data sets. I didn't say how many samples you should use. The only rule here is if you use more than the data set actually has, then it might give you a with replace false, with replace true warning. I forgot, for some reason I blanked on the word warning. We'll do 100 here. We got to predict ERA, so my target in this case is going to be ERA. Okay, so that's my target. My features, we're going to use strikeouts per 9, that's K9. Woof, woof, woof. We got walks. I'll just type in the word walk here. We got home runs, home run. And we got FIP, which is FIP. Oh, and it's not full bracket, it is FIP. Okay, now we're gonna use linear regression. Model equals linear regression. So we initialize that model. We're gonna say model fit using the train data set. We access our features, and then we'll also train, and then we'll get the target. And remember, this feature set, this is a data frame, so this is a list inside of our loc. And then target, this is a series, so we're looking for this column of data, the series in pandas. And this is the model training, right? Model train, or the model fit. And then we do a model predict. And then we're predicting on the test data set, right? So it says predict ERA in the test data set, all right? Predict ERA in the test data set. So using the test data set, same notation here, features. We're using the exact same features, and the output will be the estimated target, okay? And I'll just put that in test. And then I use the F string for my target. And then I call this target pred, because this is not the actual target, this is the prediction of the target. And then visualize by showing actual ERA on the x-axis and predicted ERA on the y, display R² and RMSE. So we do R², Pearson R. This is from the other day when we were doing the stats. We'll go test target, and then we're comparing that to test F string target pred. And then that first index is where the R value is. asterisk asterisk 2 to get the square, or the raised to the 2 squared, or the square. Is that what they call it? Power of 2. Then we get the mean squared error. Same notation, but in mean squared error, it doesn't give you a p-value. It just gives you the value of mean squared error. So we're going to raise that to the 0.5, because when you raise to the half, that's the same as square root. So that's root mean squared error, not just mean squared error. Okay, then we plot. So let's visualize. I'll use a reg plot instead of a scatter plot this time. Test, X is our target, Y is our target pred. Our title, we'll make some title text here. 1, 2, 3. 1, 2, 3. And this is R squared. And this is an F string. R2, and this is round. Round to the 3, and then RMSE, same thing. Round, RMSE, 3 decimals. Okay. PLT that title. No difference. No difference there. Just style. I tend to switch between both. That's just bad habit, to be honest, by me. Some people use single quotes. Some people use double quotes. I will say in some languages, single quotes and double quotes might make a difference, like certain columns in using SQL or Spark. Double quotes might mean specifically string type or specifically some sort of string accessing type of data. Whereas single quotes might mean something a little more general. So it just depends. I tend to switch between both because I'm lazy. But if I went to code review, one of my code reviewers would probably say like, yo, you're doing a lot of switching up of different notation for strings. Don't do that, right? So good call out. You're not wrong. Okay. So this is a one-shot answer, everything in one all-together cell of code. So I got my train and test, random state 10 and 20. I used 100 samples here. My target was ERA. My features are what the homework wanted, which is strikeouts per 9, walks, home runs, and FIP. So K per 9, walk, home run, FIP. We got the model, we initialize, then we fit, and then we predict. Then we got our statistics here, R squared and RMSE. That's what was asked to be displayed, R squared and RMSE. I put that all in a title text, which we shove through our title function while we visualize our test data set. Looking at our target, which is ERA, and our target prediction, which is ERA pred. So R squared, given all these values, comes out to 0.416, RMSE of 0.954. So if you got that, or got something really close to that, that's probably good. Okay, so that's homework. We're gonna do 2 things, chat. We're learning basically the same concept, just 2 different ways. You know, like, you ever go to a restaurant and they're like, hey, this is broccoli 2 ways. I'm gonna do the same except for data science. I'm gonna show you ways to split your data in 2 different ways. Okay, so a couple things we need to do before we get going. Well, first thing, let's always check to make sure our data set looks the same. We got a bunch of stuff in here that you've been working with. ERA is in there, of course. FIP is in there. Okay. You should have maybe a few other columns from previous homework or previous lessons. If your data frame, your ERA data set looks like that, then we're doing pretty good. Okay, we covered so much yesterday. We covered so much on day 6. Day 7 is going to be... I'm excited to do 7 this way because it makes me feel like I'm going to focus a lot on the research methods here. First thing, let's import some stuff. So from... and we did this before, but just in case you're doing your home or your days a little out of order, we are loading in linear regression. And we're also going to import from scikit-learn. I'm going to import from model selection something called train test split. Train test split. So we've been splitting our data sets with just a random sample, right? And I said, like, let's not worry about overlapping data. Well, in the real world, like, overlapping data is bad. Like, if you have a training data set and you're trying to predict what's going to happen tomorrow, but you have, say, your model was trained on, like, 2020 data, and you're trying to predict 2023, or sorry, 2020, you're trying to predict 2021, and you had, like, a few days from 2021 in your 2020 data set, well, now it's not really even. Like, you're trying to do a prediction on a complete year, but you already have some of your year in your training. So your model has already seen or already knows that data. It's able to estimate that more closely when really it shouldn't. So we call this, there's a lot of different names you call this, but generally this is what we call either overfitting or data leakage. So if you aren't particularly safe with how you're splitting your data up when you train your model, you can overfit your model. You can make it so your model is seeming to be really, really accurate when really it isn't that accurate. And so to avoid that, we're going to learn a little research methods today on how to separate your data so you don't run into that problem. And so even when you have a full data set and you're making predictions, you're going to be able to say, well, the predictions in this model are all out of sample predictions. And that's going to save you from overfitting. That's going to save you from all these different things that might ruin the validity of your model, especially if you use it on new data or other data. Okay, so a little more research methods tonight, but it's going to help you really get the complete picture of what your machine learning pipeline should be like should you leave this boot camp and try to do data science on your own. Now, before, when we were doing train equals ERA sample. Thank you, Hector, for the 100 bits, man. Random seed equals 1. And we did test. Random seed equals 2. Random seed. What was this called? Not random seed. Random state. Yeah, state. So, some of you may have done this. Like, if you wanted to see, like, oh, train, we have all this stuff here. Test, we have all this information here. Some of you may have got curious. Some of you may have got curious. And you may have wondered, what is the difference between random state 1 and 2? Is it possible that there's overlapping information here? So one way to check, and we've done this before, this was actually a homework problem. If you didn't do this, it's okay. But this is one way to see whether your data had the same information in it as if you merge one data set onto another. If you do this inner join, I think when I ended the stream, I was saying like the train data set and the test data set, since there's 600-ish samples, we should get anywhere between like 10 and 20 of the same overlapping data. So here we are with 15 names that appeared in both data sets. So 15 names that appeared in the train data set and 15 names that appeared in the test data set. For these 15 names, since they would be in the training data set, since they would already be known in the training data set, in particular, these 15 names would be overfit. There would be more information on these when we ran these over the test set. So we need a way to separate our train data set and our test data set so we're not we don't have information in the train data set that we don't really actually want in there. So we use this function called train test split, which does exactly what it sounds like. We're going to split our train data set and our test data set so we don't have overlapping data like this, okay? And this is a scikit-learn function that does this for us, okay? And it's pretty easy. So if you have a train data set and you have your test data set, you could do your train test split, ERA, and then you could set your random state, and we're gonna set that to 1. And that's it. You run through this, that's one line. It's just easier really than this. So in one line, I've split my train data set and my test data set. And when I look at my train data set here, here's my data frame of train data. And we look at my test data set here, I have my test data set. And now when we do this exact same thing, if I merge my train data and my test data after doing my train test split, notice how no names pop up. So in my train data set and my test data set, there is no overlapping information in my training data, which means when I train my model, I'm training on all the information that I have, except for the information that I'm going to collect predictions on, right? So this data set knows about everyone in my train data set, but doesn't know anything about the players in my test data set because they're two separate pools. One more thing that's good about our train test split here, remember that in our initial example, we were doing just a random sample of 100 players in each data set, right? With our train test data sets now, you could actually see in my train data set, it's actually 474, not just 100. In my test data set, I'm actually getting the remainder, 158. And if you're counting at home, like, wow, that sounds kind of like some sort of 80-20 split. Well, you would be correct, because the train size is set to 25% of the data will be in the test data set. So 75% of the data is in the train data set, 25% is in the test. So we're using the entire data frame in our train and test split. So if we copy kind of what we did for our homework, if we take a visualization, we take our R squared, Pearson R, we take our test data, target. Oh shit, actually, we can't do that yet. I skipped a step. So if we're going to set our machine learning model up, we'll do this, target, and then our features. We'll use FIP and K per 9 like we have been in the previous lessons. Make our model. That's linear regression. Model fit. We'll use our train data. So we'll do the test. Okay, so I'll make some notes here. Target, create our features and targets. Load, initialize, train, and predict. Apply statistics. Right? Okay. Nice. So this is now your pipeline. Now we have all of the data training, and then 75% of the, or 25% of the data is on the test. If we compare this to, say, well, we don't even have to compare it this way. If we take the same information from this cell, right? We did everything in here. Got the target, fit to the train and test. Reporter statistics. If we took this exact same thing, we did it up here. Okay? Or we create our train and test, and then it does it all for us in here. Like, look at how this 0.367, 1.28, and then we have this information now, 0.41, 1.097, right? So notice the difference in the loss in particular. Here, 1.28 is lower, less loss than 1.097. Now, remember the issue, right? This is more data, but also the train and the test split, there isn't repeating data inside of the training data, right? Here, you do have information that's repeating, and you have some predictions that are just going to be like dead on. And that's because this information from this data set has 15 pictures that are in both data sets, right? So this could be another way to see, okay, well, there's representative data in both. That must mean there's probably a little overfitting, right? Kind of like cheating, exactly. So in this case, we're not copying off the future, we're not copying off our neighbors. It knows all the information only from one set of data and is predicting on a completely different set of data. Okay. So that's train test split. Okay, so the advantages here, right? It allows us to, instead of doing it where we're randomly sampling and applying our rules or machine learning to a data that may or may not have the same data in it, we're now doing the train test split, and then going through our modeling pipeline here. And now we know, right, there is no overlapping data in either data set. So we are free from data that is maybe being overfit in the training. And presumably we could have done train test split as part of the model code. Exactly. So if you took train test split here, and you just want to plop that down in here, and you just run through it, you're going to get the same thing. You can run this as many times as you want. It's really fast. Linear regression is a very fast process. The train test split is also fast. And you're going to get the same answer every time here if you got whatever data set you have in here, since we're setting our seed. This is the robustness of machine learning and making variables and making reusable code. That way, when you have a new project, you don't have to start from scratch. You've seen me now over the last handful of days steal from myself. I'm just taking gigantic chunks of code and copying and pasting it wherever, and code is just flawlessly running. That's because the variables are staying consistent. The things that you change, they're attached to a variable. The way you get data, we're attaching that to specific names, variable names. And that's all being fed through the same parts of our modeling and our statistics pipelines. Even the way that we're doing our visualizations, we're not calling specifically any target X as a string, and we're using F strings to replace the other predicted targets, right? Okay, so train test split, the pipeline is built out so we're able to predict on the test data set using all the train data set. All right, we're reaching the end here, but there's a lot of time because this next thing is a little complex. We are going to be combining we have learned into this new function I'm going to teach you. This, in my opinion, is the most important thing in the machine learning part of this bootcamp. So if you made it this far, great. But the big question in everyone's mind that's probably lurking is, well, we're able to predict on 25% of the data, but you're telling us that 75% of the data is inside this training data set. What if I wanted to predict on my entire data set? What if I have all of these rows and I want out of sample fair predictions on all of these? And you might be thinking to yourself, if I do train test split, is there a way to kind of loop over it or make it so my training data set is different than my test data set and I'm able to capture all of my data set in out of sample predictions, right? In test data predictions. And if you're thinking, well, this is only 25% of the data, how do I get my 75% out? Look no further than k-fold. So let's, from scikit-learn model selection import k-fold. If you're fancy, in model selection up here, you could do train test split, comma, k-fold. You could load in multiple packages from the same class, multiple functions in the same class. Just comma separate them. Okay, I'm gonna throw a lot of shit at you right now, chat, and all of it is like pretty detail specific. So if you're like, yo, I'm not really a detail Andy. I need you to be a detail Andy for the next hour, okay? Because there are some nuances that are very difficult for me to describe And one of these things, setting the index, I've tried to prep all of us for this day. I know it's gonna get a little goofy. All right, let's just take a look at what kfold does. So first, just like anything in scikit-learn, kfold is not a model, but it's a helper function, which is gonna allow us to loop over a data set. And what it wants to know is, K is how many times you want to fold, right? And a lot of the times you might hear something like, this was a 3-fold cross-validation. This was a 10-fold CV. The amount of folds, 10-fold, 3-fold, 5-fold, 20-fold, however many folds you want to use, is actually this number right here. It's n splits, right? And the default's 5, right? The default's 5. If you don't do anything, it's going to give you a default of 5. So default 5. So we're going to fold over 5 times. And then something that's really important to know is you generally, not always, but almost always, you want to shuffle your fold. So remember, if we take our ERA sample, and we sample just 100, if we sample 10 names, right? Every time we would sample, it would sample 10 different names. So this is what we call a random shuffle, right? A random sample, a shuffled random sample, right? So we want to shuffle our data. Just like a deck of cards, we want to make sure our data is all shuffled up. That way we're protecting against anything that might be linear or sequential in our data set. Say the data set came to you like from Fangraphs or from Baseball Reference, and it was ordered top to bottom in order of war, right? Like how much war or how much ERA or how much FIP in some order. There might be some information just in the ordering, right? So in order to protect against information due to the ordering, let's shuffle through our data because we don't want the model to learn what order the data's in. We want the model to learn based off the features we're giving it, right? So let's do a kfold of 5. Let's shuffle true. And let's just loop through this. Do we need to set the seed? Yeah, let's set the seed. Let's all do a random state. Let's do random state 1. That way it's the same for all of us. If we do kf split, this means like split, like train test split. Okay? So we're going to do train test split, or in our kfold, we're going to split our data set. And notice how we do the train test split here. Do train test split the data set. It's the same here. KF split and the data set. Now, if you run this, you just get this generator object back. Something in our temporary space is not doing anything quite yet. We need to put some more stuff in here for it to iterate or work. So let's put this in a for loop for train index, test index in kf split. We can actually print our train index, right? And then we could also print our test index, right? And if we go through this, what's gonna happen is we're folding over our train test split, and we're gonna get our train index and our test index. And you're gonna see that this is just the index values. So think about this like the row values. Remember all the way back in the Excel days, or in Google Sheets, in the dataset ERA, which we have 632 rows. Our kfold, it's gonna sample 80% from for the test data set by row. So look at this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12. And then the test data set, it's going to sample the other 20% for the test. So 0 and 11 are the first values there, right? The first value here is 1. And since pandas is 0 index, this would say, all right, give me the first row. Give me the 11th or the 12th row. I guess the 10th row. Give me these rows for the test data. And then give me these rows for the training data. So to answer your question, if you're using a train test split, or if you're using a random state shuffled k-fold, really you shouldn't be getting any leakage from one data set having one random row pop out to the other, unless, for whatever reason, the row numbers end up being the same somehow. Like you have 2 row 5s. And I'll show you why that might be possible in a second. So each of these shuffles, this goes through 5 times, right? And you'll see that 0, right? Here's a good test. Haha, test, get it? Test, train test. Notice how 0 here is represented 1 time in the test data set. And you know it's the test data set because it's the smaller data set, right? This is the 20% fold. This is the test data. So here's 0. But notice that in the next iteration, 0 is here in the training data set because it's the larger data set. 0 is also here in the training data set. That's twice. 0 is again here. This is 3 times. Right? And 0 is also here. And that's the 4th and final train data set. Or I guess 5th and final train data set. Right? So 0 represented 4 times in the training, 1 time in the test, right? And you can do this for any number. Numbers 0 through 631. And you will find this is being represented in the test once, twice, not here, 3 times, and 1 last time, right? So it will shuffle through, fold over the data where 1 row is used 4 times, and then if we're training, and then that same row is going to use this test for 1 time, right? That's the beauty of the k-fold. So just like train test split, where you're splitting your training data set and your test data set, and they aren't overlapping. Now we are doing this 5 times, and we're representing the data, the training data set, separately from the test. And this will allow us to predict 5 times, save those 5 times, and append that or concatenate that to our original data set, and now we have predictions for our data frame with a model using only out-of-sample predictions, right? So all those predictions were saved out-of-sample predictions. We're not training data and also testing on the data we trained in one fell swoop. We're not doing that. We're training on data, and then we're testing on completely different data, and then we shuffle that so we can represent all of our data set evenly and accurately. If you look at our ERA, notice that we do have an index, right? And that index goes all the way to 631, right? Just like how 631 is the last value in the indexing in our k-fold split. So the theory here is we're going to create our train and test split, our train and test data sets, but instead of just a one function like this, it's going to look a little more like this, where we're going to take our ERA we're going to look for specific rows and use those specific rows as our training data and then our test data. So let's do that. So train equals earray.loc, train index. Okay, so just like how we do array greater than, less than 2, number of pitches greater than 0, you could just select rows by number, right? If I wanted, say I wanted row 627, and we did this, I think day 1 or 2, right? I could just type in 627. So if I have a list of indices, I could just shove that into my loc, right? So this is going to be my train index. I'm going to do the same for test. So I have a train data set and I have a test data set. Just like how we had our train test split, just like when we did our sampling. It's the same thing. Now we're going to copy over a lot of code. So remember, create our targets. This can go outside of the loop, right? We don't need to do that every time. So I like putting it at the top. Call this make k fold or initialize. Okay. Then we're going to do the initialize, train, and predict step. And then we'll do these steps at the very end once we predict over all of our data. Okay? So we have all of this information now, and we're adding this back to our test data set. Well, there's a few things we want to do that's a little different, okay? So for example, every time I loop through this, it's gonna overwrite our test data. So I need to save my out-of-sample predictions somewhere, right? So I'm going to create an empty out-of-sample series. Okay, I'll call this OOS preds. This is my out of sample predictions, right? Think of this as like when we create a column, when you initialize a column in a pandas data frame, sometimes we've been doing like ERA FIP equals 0, and then we fill in the FIP somewhere else, right? Or ERA left-handed pitcher equals 0, and then we fill in all the places where there's a left-handed pitcher, right? In this case, it's going to be the same thing, except we're going to create a series, initialize that series, and then we're going to append or concatenate our data to this data set, because test is going to always overwrite itself in the loop. So we need to store something outside of the loop, collect all the information outside of it, and then join it back later. So the way we do that is we're going to concatenate, okay? So we're going to concatenate, and we're going to use a function called pd_concat. Really tricky naming here. And the way that pd_concat works is it's going to take the thing you want to concatenate, right? Think of it kind of like joining, except with rows instead of with columns. The thing you want to concatenate, and then what you're going to add to the bottom of it. So in this case, I want to take whatever's in my out-of-sample predictions, and if it's nothing, that's fine. And I'm going to concatenate, comma, I want to concatenate my my target. Again, we're just looping and folding over our data. So where originally we just did a train 10 split 1 time, we're going to do this 5 times. So to do it 5 times, we're going to loop over our data 5 times. We're going to fold over our data 5 times. So now we have train test split. We have our model. We attach our model predictions back to the test data set. And then we're concatenating that test column of data. We're concatenating this up into the out-of-sample preds. And you could run this now. And you get this warning like, the default D type for an empty series will be object instead of float. Specify the D type to explicitly silence this warning. Sure, dude. D type. Float. Let's do what the developers say we should do, so we are in compliance. And now if we look at, out-of-sample predictions, we take a look at this. Here's length 632. So it's all of our data, not just a test data set. And it's all the predictions, and each prediction wasn't in the training data set, right? So these are all predictions where this was out of the testing data set, or out of the training data set. This was out of sample, out of the training data predictions. And finally, if we say ERA, target pred, equals OS preds. Pandas has some behind-the-scenes magic, where even if the rows are out of order, if there's an index on the variable, or on the series, it's going to automatically join onto the index. So if you go here and look at ERA pred, notice we have 582 and 260 instead of 428, right? Because 260 is index 1, right? And if we look at what 11 is, look at the top 20. 11 would be 428. So here's 11. Here's the pred, and here's 428. Okay. And you can kind of put this all together like this. So now, we have a new, totally completed machine learning pipeline. You have your target and your features. You have your k-fold. That way you're going to fold over your data and save your out-of-sample predictions. You have a for loop. We learned about for loops a few days ago. We create our train test split. We did that last week, or we did that yesterday in the bootcamp. And I showed you how to do it again today with train test split, the function. We have our model. We did that the other day, yesterday, last day. We did it again here. We predict and we save that back onto our test data set. Then we append or concatenate all of this into that out-of-sample predictions series that we had initialized originally. We do all of that. And then we join that all back after the for loop is done. After we've looped through 5 times, we put that back onto the main data frame, our ERA data frame. Now for the stats, it's the same thing. This is actually the easy part now. We're going to grab that first index, get to r squared, square that r term, RMSE, same thing, except mean squared error. And then we're going to grab our pred predictions, raise that to the half, to root mean square error. We'll make our title string. Triple quotes, that way we could separate it on our separate lines. R squared. Curly braces, that way we could input a variable. We'll round R squared. The 3 decimals. Same thing with RMSE. Let's create that reg plot. You could do a scatter plot if you want as well. That data set is ERA. X is our target, and Y is our target pred. Now remember, target pred is out of sample predictions now. It's not test. We're not doing this on the test data. Right? Before we were just doing it on test data. Now we got the full-blown entire data set. All of the ERA data set, all 600 points. Look how many more scatter points there are, right? Versus this. Right? Just in terms of 100 versus all 600, however many they are. And this is all out of sample, right? It's not overfitting to the same information in the test data set and the training. We did the train test split using k-fold. We have our R squared. This is a 0.391, right? We've been seeing numbers like that, anywhere from 0.35 up to 0.4 something. An RMSE 1.05, we've seen everything from 1.02 upwards to like 1.1. So this is in the ballpark, but now we can say 2 things that we weren't able to say before. The first thing, we're not overfitting our data where we're using the same data in the training sample and the test sample. So we could say that because we're using train test split. And 2, we are using all of the data. We're not just using 75% and then testing on 25 and calling it a day. We're folding over 5 times, predicting an out-of-sample prediction for each row. And now we could represent our entire data set this way. If you're here, you're listening to my voice right now, we did it, chat. Congratulations. Let's take a look at what y'all have done in the last 4 weeks. We started here. Y'all remember? Not only did we start here, but this is where you started. Some of you didn't know Python. Some of you had no idea. Some of you maybe have downloaded it, tried to mess around in it, but you didn't know Python. Then, after 100 people left because they couldn't actually get the data, we imported OS, looked for materials, imported pandas. We checked to see what version of pandas we were using at the time. I showed you the very, very basics. X equals 1, Y equals 2. We loaded in our data frame. This is the first time for some of you loading in data through pandas. PD read CSV. And you load it in at CSV. And then the first time you saw data in Python for some of you, df.head. That was the first thing. And then you saw that data frame pop up. That same thing in here. We created total score, home score plus away. We created isStrike, and that's what we did here. How you added your first 2 columns in pandas. How we created a variable of strike events We looked through those strike events, and we created whether or not something was a strike. Then I gave you your first homework. Day 2. We went over that stuff again. We looked for is Red's picture. We did that in the Google Sheets as well. We looked for when a picture was a Red's picture. I showed you that you don't have to just take the top 5 rows. You could take 50 rows if you want. Then we did the group by. The first time we did aggregation because we were mimicking, right? The pivot table. Day 3, pivot table. Then we introduced renaming columns. Then we did the average. Then we did the count. And then I showed you, yes, that's what we did in the pivot table, the average and the count. Yes, yes. Then we merged that together and we created that same data frame we had. We created some data visualization using Seaborn and Matplotlib. We also created that data visualization here. Then we wanted to create this multiple times, right? We tried to do this twice, but we had to click through a bunch of shit. And then I showed you the power of doing this in the programming language. You could just change out the name. Make plot lib, yes. And then we introduced the for loop. Maybe for some of you, the first time you ever did a for loop. Notice how we cheated. You know, we did the print picture name. Remember, now we use a plt.title. You didn't know that yet. You didn't know that was going to go on. You didn't know that was going to go on. Lots of homework, lots of data viz homework. Day 4. Day 4 was when shit got super real. We left the world of Excel. We left the world of spreadsheets. Instead of using the 49,000 rows, we went up to the 700,000 rows. And the reason we do that is because it's hard to do that in Excel. This is another advantage of Python and computer programming in general. You can store a lot more data and it lives in the background, and performance is not compromised when you load in a ton of data. Did the is strike stuff, we did all the stuff we did on day 1. And then we also created run scored. We also limited down the data so we didn't have to use all 700,000 rows. Then we created ERA. This is the beginning of our ERA data frame. And we started using those skills that we learned on those first handful of days. Group by sum. Did some value counts. Created all of this. And then we learned how to merge. We started doing joins and merges. Created an ERA. This was the initial ERA data frame. Isn't that weird to see it like this? This is what it looked like to start. Then create the ERA data frame, create the ERA, put in strikeouts, did K per 9, which we've been using pretty much the entire time. Created some walk events, created some home run events, more group buys, more merging, and then I showed you an alternative way to do some of the math. Showed some statistics, statistical description, descriptive stats, mean, median, and mode. Then we showed some correlation for those who are doing some business statistics. Maybe you needed a plus scale or a 100 scale value. So how to do that. Some histograms, some more data visualization, and then of course, our stats for the academics who are in here. How do you do Pearson R, R squared? If you did some non-parametric stats, Spearman R and R squared. How to do a t-test. Where the t-value, the p-values are, how to index through. This is where we showed Python indexing in an output. More scatter plots. And then this is where we started introducing titles, right? And then I showed you triple quotes. Another way to do strings. And this is also where we tasted train test split. And we also tasted making a function. Then yesterday, for loop through the correlations, made all these different plots. Then I said, you know, it's fun doing it with one variable. What if we used all those variables to predict ERA? We busted out some old school math. Y equals mx plus b. Linear regression. And I showed you how to put in your targets and features appropriately. That way we could use our linear regression fit and then rip out, after you train the model, what the intercept is and the coefficients for all your variables. And then by hand, you know, like those math classes that make you do it by hand and they show you the shortcut. I kind of did that. I kind of did that on y'all. Showed you how to do it. That way you would believe me when I said it does it. It's real. Some of y'all might be like, how do you know? Well, there you go. We did y equals mx plus b. That's how you know. How to do it for more than one feature. We also did it by hand for this. Emphasis on the for loops again. Need to make sure that you guys don't forget that because the next day we're going to use for loops in a big way. And then I say, yo, you don't have to do it by hand every time. Just use the predict method, the predict function. Makes your code a little cleaner. Go back to train test split. And then we do our train test split using our new model fit and predict. And that's your first sampling of out of sample testing. And then today, we did train test split in a function. Not just one function. We did in two. We did train test split, and then we did k-fold. Fold through 5 times, you shuffle that. And then you're saving your out-of-sample predictions outside of that loop. Use that index, train test. Shove that into your linear regression. Predict out. Concatenate that up into your pandas series. Join that back on your main data frame ERA. And then plot it. And now you're doing machine learning. And now 10:14 p.m. on a very warm, humid Cincinnati Thursday. Bootcamp is over. I don't have a speech. I don't have anything to say to y'all outside of good luck. Because at the end of the day, you could have learned this in a million ways. You could have read a book, gone to a class, bought into something like DataQuest, done some open online free thing. You could have done any of that, but you chose to be here. And for whatever reason, if you made it this far, you can program. That's in your wheelhouse. You shouldn't be afraid of data science. You shouldn't be afraid of Python, or if you end up moving into R, if you end up moving into Rust, if you end up moving into Julia, it's in your wheelhouse. You have some fundamental skills now. So good luck. Use those skills. Don't let them go to waste. Do a project. Win fantasy football this year. Update your projection system at your work with linear regression instead of moving average. Let your friends know you know how to program now. Brag about it. You did it. You made it this far. You're listening to this. It's not if you can. it's you can.